Welcome again. Today we look at hybridization in topic 14.2 for IB Chemistry HL. Hybridization is a term used to describe the mixing of atomic orbitals to produce equivalent hybrid orbitals. The idea that an s orbital and a p orbital can combine to make equivalent orbitals cannot be observed in the lab, but it is based on mathematical models. The Schrödinger wave equation provides a mathematical model to help explain bonding and symmetry that can be observed experimentally. So as we look at orbital hybridization, we must think of this explanation of mixing of orbitals as a mathematical model to explain what we can observe experimentally in molecules like CH4, methane, which we know contains 4 equivalent sigma bonds. Carbon, with its electronic configuration shown here, has 2 electrons in its 2s orbital and 1 electron in its px1, 1 electron in its pxy, and none in the 2pz orbital. But 1 electron is promoted from this 2s orbital up to the empty pz orbital, and this allows for 4 electrons to be present, 1 in the s, 1 in the 2px, 1 in the 2py, and 1 in the 2pz. These 4 orbitals then become merged or of equivalent status, creating Sp2 hybrid orbitals, S, 1, 2, 3 p's, all of them joining to form an equivalent set of 4 orbitals, creating 4 electron domains, and it is these 4 electron domains that allow for Sp3 hybrid orbitals. CH4 is just the simplest example that we can provide to explain Sp3 orbital hybridization. Here you can see the 4 equivalent sigma bonds formed as methane takes on its tetrahedral shape with a bond angle of 109.5 degrees. But if it is that 4 electron domains allows for Sp3 hybridization, then it would be true also that the oxygen atom in the water molecule also provides an example of Sp3 hybridization, because the 6 valence electrons in oxygen distribute themselves throughout the s and the 3p orbitals, and again the 4 orbitals combine. But in the case of the water molecule, only 2 of these electrons engage in bonding. The other 4 electrons occupy their own electron domains. 4 electron domains exist as a result of the S hybridizing or joining with the 3 P's, creating an electron domain geometry that is tetrahedral. And although the water molecule itself has a bent molecular geometry, it has a tetrahedral electron domain geometry. So once we get these 4 electron domains and we get the tetrahedral electron domain geometry, then it follows that we have Sp3 orbital hybridization. What about the case of ethene, which has been experimentally observed to exist as a trigonal planar molecule? In this case, only 3 electron domains are associated with each carbon atom, and the explanation for this lies in what is termed Sp2 hybridization. Only the s and 2 of the p orbitals coalesce or hybridize to become equivalent, leaving 1 p orbital free and unhybridized. And it is this p orbital on each of these carbons here which overlaps with the other p orbital to form what is termed as a pi bond. The pi bond does not exist in its own electron domain, but allows for the existence of what is termed a double bond. Experimental observations will show that this double bond is stronger than the single bond, and the bond length is also shorter than the single bond. And the explanation for this trigonal planar molecule with the stronger bond and the two sigma bonds can be had through what is termed Sp2 hybridization, where one s orbital merges with the two p orbitals to form Sp2 hybrids, one s and two p's, creating these three equivalent orbitals. These three equivalent orbitals, 1, 2, and 3, engage in sigma bonding, leaving the free p orbital here on each carbon to engage in pi bonding. And this is the explanation for the trigonal planar structure of ethene. Another molecule like BF3, which has only 3 valence electrons, also engages in Sp2 hybridization, showing that the existence of 3 electron domains is associated with Sp2 hybridization. These 3 electrons in boron occupying the s and the 2p levels with an empty third p orbital. So these 3 hybridizing to give us 3 equivalent Sp2 hybrid orbitals that allow for the trigonal planar structure seen in a molecule like boron trifluoride, which has a bond angle of 120 degrees. Finally, we consider ethine, which has the formula C2H2. In the case of ethine, experimental observations show an even stronger bond between the 2 carbon atoms, a triple bond. And here we have only the 2 electron domains. The explanation using the mathematical model for this phenomenon is termed Sp hybridization. Here, just the s orbital and one of the p's form 2 equivalent Sp hybrid orbitals, which engage in sigma bonding, leaving 2 other electrons to engage in pi bonding, overlapping to form the strong triple bond. Here we see the existence of 2 electron domains, one domain for this single bond to the hydrogen, and the other domain for the triple bond between one carbon and the other carbon. 2 electron domains, Sp hybridization. Another example of Sp hybridization can be found in beryllium chloride. Here, beryllium, which contains only 2 valence electrons, has Sp hybridization, forming 2 equivalent orbitals which engage in sigma bonding. And the molecule takes on a linear shape. That linear shape is consistent with the shape observed in ethine. So the linear shape results from 2 electron domains, and that can be explained by Sp hybridization. The trigonal planar shape results from 3 electron domains, and this can be explained by Sp2 hybridization, s and 2 p's. And of course, the tetrahedral shape observed in CH4 shows the existence of 4 electron domains, which can be explained by Sp3 hybridization, s 1, 2, 3 p's. Methane, Sp3, tetrahedral electron domain geometry. Ethane, Sp2, trigonal planar electron domain geometry. And ethine, Sp, linear electron domain geometry. The phenomenon of orbital hybridization is really a mathematical explanation for the shapes of molecules that can be observed experimentally. What type of orbital hybridization exists here with this nitrogen atom in ammonia, NH3? And what type of orbital hybridization exists here for this carbon, this oxygen, and this nitrogen?